All right, class. So this week we're talking, everything's about probability this week, and we're going to look at it as it relates to statistics. So, with probability, normally when you're looking at like the likelihood of some outcome, your values for probability range between 0 and 1, right? Where 0 is that the likelihood of the event occurring is 0, right? It's impossible. To 1 being that the likelihood of that event is 100%. Couple of different ways to kind of think about and look about probability. There's the analytic view and kind of a frequency way of looking at it. And the frequency way plays more to the statistics that we've been looking at. But the analytic view is you can calculate a basic probability. So as an example, let's say we take a sample of 100 people, and we want to know out of those 100 people how many of them are lactose intolerant and how many are not. And if in your sample, let's say that 65 of the individuals say that, hey, I am lactose intolerant, so they're LI. We can figure out what the probability of someone having lactose or being lactose intolerant is, right? If 65 are, then we know that 35 are not. So this is kind of group A are these folks, group B are these folks. So if I want to know what is the probability of someone being lactose intolerant, I can take, well, there's 65 folks in group A, and then between group A and group B, 65 and 35, that's 100 individuals, right? So the probability here, this divides out to be 0.651, which does fall within that range, right, of 0 to 1. Or another way to say this, instead of saying that the probability is 0.65, you can say you have a 65% chance of being lactose intolerant or having some type of intolerance to dairy products, right? So that's the analytic way of thinking about it. You take how many individuals in your sample have a certain trait divided by the total number of individuals, okay? And that's the analytic view. And it plays in really similarly to the frequency view. So here on the right, I have a frequency distribution where we're looking at, okay, how many hours of exercise do individuals get? And I just made these numbers up. And so we're saying, okay, a half hour, hour and a half, 2 hours, or more than 2.5 hours. And let's say we took a sample total of 50 individuals, and this is how I broke out. 10 of them elected this option, 12 fell into this option, 5 here, 13 here, right, and 10 here. So we have all these frequencies. We know that, for example, 5 people said that they exercised about an hour and a half every day. And so if I want to know what the relative frequency is for each of these things, well, then I'm just going to take the number of individuals and divide that by the total, the number of individuals in a given category, and divide that by the total number of individuals, and it gives me these decimals, okay? And those are the relative frequencies. Well, if you think about it, these numbers, they're the exact same thing, right? This calculation is this calculation, right? It's the exact same thing as the analytic view. So if you're ever looking at a frequency distribution and they've given you the relative frequencies, essentially what they've given you there are the probabilities of an individual being in a given group and having, you know, the attribute of that group based on the sample that you're looking at. So again, if you have the relative frequencies, you're looking at the probability of whatever that trait is. In this case, I'm highlighting the half hour, right? Of the sample I took, you have a 20% of the people or you have a 20% chance of picking someone out of that group that exercises for only a half an hour a day. So frequency distributions can be really nice because the other way of looking at this is you can actually take this data that I have, right, and we could plot it in frequency versus hours of exercise, where this would be 0 and it would tick itself off over to here to 2.5 plus or whatever, and we could plot all these values and find a little one and then a kind of big one and then anyways, and here's a distribution where the height of each column is going to represent some level of probability. Okay, so lots going on with our frequency distributions, that there is this connection between the frequency of occurrence and probability. Okay, that's important. So just to kind of clarify a few terms, sampling with and without replacement. So this is going to be really important for us to understand. So let's say you have some population here, and you want to build a sample of it. So if I draw out an individual and put them in here, and draw out another one, and draw out another one, and draw out another one, okay, notice that I'm just taking things out of the population, but I'm not putting anything back in. Okay, if you take your samples this way, you're changing probabilities. Okay, let me show you maybe a little bit more of a concrete example. Let's say we have, I don't know, let's say we have 3 greens and 2 red balls. Okay, now let's take a look. So my total number here, n equals 5, and I have 3 greens, I have 2 reds. So if I took a sample right now, let's say I randomly reached in there and I happened to pull out one of these reds. So I pull out a red. Okay. Well, what would be the chance, before I even reached in, what's the chance of me having even drawn a red? Well, there are 2 options out of 5. Okay. If I don't put that red back, well, what are the chances of me drawing a red now? Well, then my chances drop to just 1 out of 4. Okay, the probability changes if you sample without replacement. Every time you draw a sample, you're changing the probability of every other. So let's say you draw again and you pull out another red. Well, now your sample only has green in it. Your probability, right? If I were to say, okay, well, now what's the probability of getting a red? It's 0 out of 3, right? The chances of you getting a red now are it's impossible to get a red. So if you're sampling without replacement, every time you take a sample, you change the probability of drawing every other thing within your distribution. But if you have a sample and you draw something out and look at it and then put it back, so now that thing has a chance of being drawn again on a second pass, then sampling with replacement does not change the probabilities of events happening in the future. So that's an important distinction. You need to know, are you sampling with replacement or without? And for a lot of the things we do, we kind of assume that we're sampling with replacement because we don't want the probabilities to change every single time we take a sample. Okay. So again, we're still kind of combing over some definitions. So independent events. So events are kind of like the results of your sampling or the outcome of some experiment, okay? So events are said to be independent when the probability of one event this should say not. does not affect the probability of another event occurring. Okay, this not is very important. That must be in there. So again, events are independent when the probability of one event occurring does not affect the probability of another event occurring. So an example of this is if you're rolling a dice and then flipping a coin at the same time. Okay, the number that comes up on the dice does not affect at all the outcome of head or tails on the coin, right? So the dice roll and the coin toss, they're completely and totally independent. What happens here cannot change what happens on the coin. Okay? So if you think back to sampling with and without replacement, if you sample without replacement, then your events are not independent. Because then your events are not independent because you're changing the probabilities of everything else behind it. But if you are sampling with replacement, then you're not adjusting the chances, and so the events are more, at least the likelihood of your study being independent is much greater if you're sampling with replacement. But this is what that's talking about. Okay. So, okay, mutually exclusive events. This is when two events cannot happen at the same time. Okay. And the example I have for this is that you can't turn right and left at the same time. You have to. It's one or the other. Okay. So, and we'll look a little bit more at like what it means to be mutually exclusive as we move on. But just that example of like you can't do both things at once. It can't be night and day at the same time, right? They're mutually exclusive. So that's that one. A little bit more simple. Okay, so the additive law of probability. So first thing to note here is that this, at least the way that we're looking at it, it only works for mutually exclusive events, okay? If you're going to use this formula that I have, the probability of A or B, right, they have to be mutually exclusive events. And so the little test that I have, or I guess the example I have is, let's say you have a pile of marbles. Now this pile of marbles has more colors in it than I have displayed here, but let's say that in your pile of marbles, right, this is what the distribution looks like. There are 2 reds, 4 blues, 3 greens, and a yellow, okay? And I could ask you a question, okay, what are the chances, or what is the probability of you pulling out a green or a blue marble? Okay, so we're looking at green or blue. If I was looking at just what's the chances of getting a green, well then I would do 3 over 10, right? Because there's a total of 10 marbles in our little, right? So we have a total of 10. And so it'd be 3 over 10 to be 0.3, right? But I want to know, so I'm changing it a little bit. I want to know what is the probability of getting a green or a yellow? Okay, so if I'm looking at this, what is the probability of green or yellow? So then I would need to take what's the probability of getting green and then add it to the probability of getting yellow. So the probability of getting green all by itself is 3 over 10, plus the probability of getting a yellow is 1 over 10. And so this is going to give me 4 over 10, or 0.4 would be my chances of getting a green or a yellow. Okay. Notice I'm not saying green and yellow. I'm saying green or yellow. And so that's really important. And it's a one draw event. So this is when you would use the additive law of probability. And notice that these events are mutually exclusive. When I reach in to draw out a marble, it can't be both green and yellow at the same time. It's either or. So let's move on. So the multiplicative law of probability. Okay, so now this is the joint occurrence of two or more independent events. Okay, so now we're looking at things happening at the same time. So again, I'm sampling with replacement. What is the probability of drawing a blue marble and then drawing a yellow marble? Okay. So it's not drawing a blue marble or a yellow marble. It's I want to draw a blue marble, put it back, and then reach in and draw out another marble and have it be yellow. Okay. So again, I haven't changed. The events are still independent because the probabilities don't change in between draws, right? So for this is when I want to use the multiplicative law. Because, what did I say, blue and yellow? So if I'm looking at blue and a yellow, so my chances of drawing a blue are 4 out of 10, and I want to multiply that by my chances of drawing a yellow, which is 1 out of 10. And so this is going to be 4 over 100, or 0.04. So you have a 4% chance of reaching in and drawing a blue, putting it back, and then drawing a yellow. You have a 4% chance of that happening. Okay? That's the multiplicative law of probability. It's the joint occurrence of two or more independent events. All right? Okay. So joint probability, okay, this is the probability of event A happening at the same time as event B. And again, for this type of probability, right? And now this is not, we can use the multiplicative law if the events are independent, okay? But the events don't have to be independent for joint probability to apply, okay? If they are independent, then we can use the multiplicative law of probability to calculate the probability of those two things happening, as we stated. So examples of this is if you're rolling 2 dice at the same time, getting a 5 on each dice. Okay, so those are 2 events, right? You have 2 separate die, and what's the chances of them both landing on 5 at the same time? Well, I would use the events are independent, right? Because the outcome of one dice does not determine what the outcome of the other dice will be. Those outcomes are separate. So I could use the multiplicative law, and I could say that, okay, 1/6 times 1/6 is going to give me 1/36 as my joint probability, and toss that into a calculator to get the decimal for that. But let's look at the other example I have on here, okay? The other example says, what about having a heart attack and a high cholesterol count? Can we use the multiplicative law? If I knew what the probability of having a heart attack is, and if I knew what the probability of having high cholesterol was, could I use the multiplicative law and just multiply those probabilities together to find out what the joint probability is? And in this second case, I would say no, because I would say that there's probably some type of causal link or a connection between having a heart attack and having high cholesterol. So you wouldn't be able to use the multiplicative law in this case, even though it is a case of joint probability, right? Just because we're looking at, here's 2 events happening at the same time, we could also be studying what is the probability of someone having a heart attack and being on the street. I think you could make a much higher case for those 2 things not being connected, of those 2 events actually being independent. But having a heart attack and having a high cholesterol count, those are probably linked and not independent events. So that's joint probability, okay? They have to happen at the same time. The last one that we're going to look at today is conditional probability. And so this is the probability of event A occurring given that event B has already occurred, okay? So kind of like it says, like there is a condition, right? Event B has to have already happened, and then I want to see, okay, now that B has happened, what are my chances of A now occurring? Okay, so examples of this are, for example, you could say, what is the probability that a student will pass the midterm given that they have studied 10 or more hours? Okay, but that's my given. So they have to have already studied 10 hours. What is the probability that a patient will get an infection given that the medical staff frequently washes their hands? And so, right, what is the event that has to have already occurred? Well, the medical staff is already frequently washing their hands, right? What is the probability that a child will take a nap given that they played at a park for 3 hours? Okay, so I'm conditioning the first event on something already having happened. So kind of as a final example to tie all of these things together is this. So now again, I just made up these numbers, so this isn't real data. So take a look at what we have here. So the information in this table follows the rules and stuff that you can kind of see. So you have, we're looking at class, so different groups of people, sophomores, juniors, and seniors, and I want to know who's brushing their teeth and who's not brushing their teeth. So let's say I sampled a total of 85 people, and I asked them these questions, and here's how the data worked out, okay? 5 of the sophomores were brushing their teeth, 15 were not, right? And so on. So what is the simple probability that a random person sampled brushes their teeth? Okay, so for that, well, I had 40 people in my sample say that they were brushing their teeth, so the simple probability here is going to be 40 over 85, because that's the total number of people that I'm looking at. So that would be a probability of 0.47, okay? Or if this data was correct, you would have, if you randomly selected a person, then you would have a 47% chance of choosing someone who is brushing their teeth. And again, so this is regardless of what class they're in, right? This is just the simple probability of that a random person is brushing their teeth or not, okay? So now let's look at an example with joint probability, right? What is the joint probability that a person will be a junior and brushing their teeth, okay? So for this, they have to be both a junior and be brushing their teeth, okay? For this next bit. And it has to happen at the same time. So if I look at this, okay, so of all the people I looked, 10 of them were juniors and brushing their teeth. So this is going to be 10 over the total 85 individuals that I sampled. Because these are the only individuals that are brushing their teeth and juniors. Okay? So that works out to be 12%, or 0.12, okay? As the probability, or you have a 12% chance of finding someone that is a junior and brushing their teeth. So then the next question is, okay, so what is the conditional probability that a person will be brushing their teeth given that they are a junior? Okay, so now this changes everything. Okay, if I'm saying given that they are a junior, I'm no longer looking at all 85, right? I'm looking at only those that are juniors. I'm saying, okay, look, my condition now is I'm only looking at the juniors. These people, the sophomores and the seniors, don't exist anymore because I've conditioned this probability on the fact that the individual is already a junior. And so now I have 10 teeth brushers. So 10, given that they're a junior, is going to be 0.33 or 33%. You have a 33% chance that someone will be brushing their teeth given that they are a junior. I hope this clears things up a little bit and showcases the difference between joint and conditional probability, right? With a joint probability, I'm still looking at the full sample. And I just need this thing to be happening at the same time. But with conditional probability, I'm no longer looking at the full sample. I'm looking at a subset of the sample based on a certain condition. And so that's really going to be the difference between those two types of probabilities. So this is all that I have for you this week. Let me know if you have any questions. Shoot me an email or post a comment. And have a great week. Thanks, everybody.